Good afternoon, everyone. Am I audible to all of you?
Yes, ma'am.
Yes.
Yes, ma'am.
Whether my screen is visible properly? In previous lecture, we have seen the concept of binary, full adder, half adder, full subtractor, and half subtractor. Today, we are going to see the new concept that is n-bit parallel binary adder. Okay, so in case of full adder, as we all know, the drawback of half adder is overcome by full adder, as the carry is not considered in half adder, which is considered in full adder. Okay, but in case of full adder can add only two binary bits along with carry. Means only 3 bits it can add, or it can perform addition of only 3 bits. But in practice, suppose you want to add 3 plus 4. Okay, if you want to perform this operation, then you need to write down the binary equivalent of each decimal number, and then you have to add the numbers. Okay, suppose here 3 can be represented by 0011 and 4 can be represented by this. And then after that you have to add this 1 with 0, and currently this is the first operation, that's why the carry is not generated here, or it is not considered here, so carry is 0. So 0 plus 1 plus 0 is equal to 1. Here carry 0 is created or generated. Carry 0 is generated. It should be transferred to the next addition. 0 plus 1 plus 0, again 1. Again 0 is generated. 0 plus 1, 1. Like this. Means we are performing this addition like this. But with the help of full adder, single full adder, we can't perform this addition. As full adder can only perform this addition of 3 single bits. Means 2 binary bits along with carry. Yes, that's why. So to overcome this drawback of full adder, means if you want to perform addition of 4-bit binary numbers, then how many full adder you need to use here? Suppose this is my first full adder. Similarly, for addition of next binary bits along with carry, you need to use second full adder. Similarly, third full adder, and this one will be your fourth full adder. Like this, if you want to add 4-bit binary numbers, two 4-bit binary numbers, then you need to use you need to use 4 full adders for addition of 4-bit binary number. Right? Understood, everyone? Or any doubt you have? Yes? So here, you can see, suppose this is your first full adder. This is your second full adder. As every time we start addition from right side to left side, we are using this full adder first. Similarly, full adder second, full adder third, and full adder fourth. Suppose, okay. Then, if you want to add, just wait. If you want to add here, then it requires 2 numbers. So these are first, suppose this is your A and this is your B. Means what? A0, A1, A2, A3. Similarly, B0, B1, B2, B3. So this is your B0 and A0. That is LSB bit of A and LSB bit of B. And you need to consider here carry in. If carry is there, then you need to consider this carry. Then sum is generated, sum is given by this line, and whatever carry is generated, it should be given as input to the next full adder. Okay, so here C in of suppose C1. Okay, then that C1 is given as input. Again, 2 inputs are there, that is A1 and B1. C1 is also one of the input for this full adder second. Sum, that is S0, S1. Then this carry, this one is S1 and this carry is generated. It should be given as input. Like this, you can perform addition of n number of inputs with the help of n number of flip-flops. Not flip-flop, n number of full adders. Yes, everyone understood this. If you want to add, in practice, you don't add only 3 single digit. If you want to add n number of bits simultaneously, Then you need to use n number of flip-flops for addition of each 3-bit binary numbers, including carry. Yes, everyone understood this? Or any doubt you have? Yes? Simply draw this diagram. Again, suppose here, first suppose functioning is completed, means this full adder takes input A0, B0 and takes C in, okay, and generate outputs. Outputs will be sum and carry. So it gives this output S0 and generates carry 1, and that carry will be given as, screen is blurred. Okay, so this carry is generated and it should be given as one of the input or carry input to the next flip-flop, not flip-flop, next full adder. So the propagation delay is included here, means some time is required to travel that carry out from first full adder to carry into the second full adder. Okay, so for that purpose the propagation delay is generated, and when you add that propagation delay, then you will get the exact time required to complete this addition. Okay, suppose here two inputs are there and you have to use this full adder, 4-bit binary adder. Okay, then suppose total 10 microseconds are required to travel the carry generated from previous addition to the next flip-flop. Okay, so here first full adder is there, and this first full adder generates carry, and that carry is propagated to the second full adder to add that addition. Okay, to get that addition, then and that particular time requirement is 10 microseconds. So total time required is 10 into 4, that is equal to 40 microseconds. So total microseconds are required to perform this addition is 40 microseconds. And plus you can add the processing time required to add this 4 or 3 numbers that is used by the full adder. Yes, everyone understood this? So you should know the concept of 4-bit parallel binary adder. What is the use of that adder? Then second thing is what? Why propagation delay is generated and how that is calculated. With the help of this example, you can calculate the propagation delay. Here, the propagation delay is given for only first flip-flop. Then, how much time is required to complete this procedure or complete this addition? Then you need to simply add here 10 microseconds, 10 microseconds, 10 microseconds, 10. 10 microseconds means what? This is the processing time, and that particular carry is forwarded to the next flip-flop input, that is carry out of first one is given as carry in of the second full adder. So this is the time given, means the total time you can't multiply by 4, as this carry is generated, it should be given here. Again this carry is generated, it should be given second. Again this carry is generated, it should be given here, and then addition. So the total propagation delay is 10 into 3 plus the processing time. So the processing time will be multiplied by 4, but here propagation the delay can be multiplied by 3 only. Okay. Just wait up. Yes, now is it visible or still blur?
No, ma'am, it's not visible.
Yes, I'm changing my network. Yes, tell me whether it is visible now.
No, ma'am.
Blur in it.
No, ma'am.
Blur it. Now, okay, I'll explain you the next concept. That is 4-bit parallel binary adder. So we can see the block diagram of 4-bit parallel binary adder and tell me whether the board is visible or not. Actually, it is reflecting. So I off the lights. Just tell me. Suppose this is a 4-bit parallel binary adder. Yes, is it visible now?
Yes, ma'am.
Yes. Okay. So this is your 4-bit parallel binary adder. So here this parallel binary adder and IC of this one is 7483. The IC number for 4-bit parallel binary adder is 7483. So this particular combinational circuit, it is also one of the type of combinational circuit. So this circuit can perform addition of 4-bit parallel binary adder or can perform addition of 4-bit binary number. Okay, so suppose here we can see initially you have two numbers, 4-bit binary numbers. So this is your first binary number, that is suppose this one is A and next binary number, 4-bit binary number is B, suppose. Okay, these are two numbers A and B, and this particular combinational circuit adds these two numbers simultaneously. Means instead of using 4 full adder, you can simply use this IC. Okay, as we have already seen that n-bit parallel binary adder, to add n number of binary bits simultaneously, we can use n-bit parallel binary adder. But here, instead of this, if you want to add 4-bit binary adder parallelly, then you can use the IC, you can make use of this IC 7483. Name of this IC is 4-bit parallel binary adder. Means it can only perform 4-bit two 4-bit numbers only. Okay, so here these two numbers are given. One more pin is given, that is C in pin. Okay, suppose I have given previous example, that is 4 plus 3. So 4 is 0 1 0 0 and suppose 0 1 1 1. Suppose you want to add these numbers, then here initially when you start adding these numbers, then you have to start with LSB bit only. Okay, so these are two LSB bit. Just check out whether Cin is there for last one full adder. No Cin is there for last one full adder. Okay, that full adder will add only these two numbers, and whatever the carry is generated from these addition, that will be given as input, that is Cin to the next full adder output. Okay, so that's why here Cin is always 0. If Cin is not given, then the LSB bit Cin or LSB bit full adder takes input Cin, that is 0. So for that purpose, this IC have one input Cin, and always remember that Cin should be connected to ground. Ground means what? Ground means 0 volt. Where in on kick 0 volt is there, you have to just connect it there. Okay. After that, C out is generated. Means what? After adding MSB bit, whatever carry is generated, that will be given from this pin. Okay. So here C out is there, and outputs are some, that is S0, S1, S2, S3 and S4. So S1 is the LSB bit and S4 is the MSB bit. Means what? If you want to add 4-bit parallel binary adder, then you can simply use these two binary you can simply use this IC, that is 7483 IC for addition of 4-bit binary number. Understood everyone? So everyone draw this diagram. This is the block diagram of IC 74. Not you can't say directly it is 7483 IC, but this is the block diagram of 4-bit parallel binary adder. Okay. So everyone complete this diagram. You can see here the internal structure of this block diagram. So here, suppose A1, A2, A3 and A4. So similarly, B1, B2, B3 and B4. And here you can see the actual structure. This is your first full adder, F1. Then FA2, then FA3, that is full adder 3, and last one is FA4. And here Cin, as we can see, this Cin is connected to ground, so permanently it should connect it to ground. Then output here, it takes two inputs, that is A1, B1, and it generates output, that is S1. And second output is C1, that should be given as input to that full adder. Similarly, here it takes another two inputs, that is A2 and B2, and it generates S2. Then here C2 is given as input here. Then next A3, B3, output is generated S3, and second output is C3. And now this C4 is equal to this C out. And this is S4, and inputs are A4 and B4, like this. So you can see this is the block diagram of 4-bit parallel binary adder, and this is the internal structure of this 4-bit parallel binary adder. Means it uses total 4 full adder. It takes inputs from LSB bit of both numbers to MSB bit of both numbers. It takes Cin, and every time you need to connect it to ground, and it gives output C out, and it gives that from this end. And understood everyone? So you can draw this block diagram and internal structure of 4-bit parallel binary adder. After that, I'll tell you the pin diagram of 7483 IC. Yes, done with the block diagram, everyone. Okay, after that you can see this is the pin diagram of IC 7483. You should know the name of this IC 7483. What is the name of IC 7483? It is 4-bit parallel binary adder. With the help of this IC, we can add any two binary numbers, 4-bit binary numbers. Okay, so here this IC having total number of pins, 16 pins are there. In this IC 7483, total 16 pins are there. Okay, till now we saw all the basic ICs and all the derived and universal ICs, but all that ICs are having only 14 pins, means 1 to 7 from left side for left side and remaining 7 pin numbers for right side. So 7 into 7 into 2 is equal to 14. So total pin numbers were 14 for all the remaining or the previous ICs, basic, derived and universal ICs. This is your first IC in your syllabus, that is 7483 IC, which is having total pins 16 pins. Okay, so total 1 to 8 pin numbers at this side and the remaining 8 pin numbers at this side. Okay, and all these 16 pins are having a specific function. We can't consider any number for any pin, okay, or any purpose for any pin. So here suppose pin number first, you can see this is a knob. Knob indicates the start of means or how to place that IC. It indicates with the help of this knob. That knob should be at the upper side always. So this is the your IC. Then the what I can say, the right side or the left side of this knob indicates your IP number first. So your pin number first is for A4. A4 means what? This is your A4. So MSB bit of A number should be connected to first pin number. So it is already reserved or the specific functions are already allocated to each and every pin. We can't connect anywhere. Okay. So A4 pin number you should connect it to 1. So you can write here pin number 1 for A4. Then S3 is for 2. Means second pin number is reserved for S3. So you can write down here 2. Similarly, 3 pin number is A4. So not A4, A3. So A3 is this one A3. So third pin number is A3. Now next is B3. B3 is 4. So you can write here B3. B3 is 4. Then 5. Remember, as like in the previous ICs, every time 7th pin number is reserved for ground and 14th pin number is reserved for VCC. But in case of the remaining ICs, it is not compulsory that 7th is reserved for ground and 14th is reserved for VCC. This IC is having total 16 pin, and out of that 16 pin, two pins are there for ground and VCC. But here, 5th pin number for IC 7483 is reserved for VCC. So every time just remember, 5th pin number is reserved for VCC. So you have to connect it to +5 volt or VCC where on the board. Then 6th pin number is reserved for S2. S2 means the second bit of output, that is S2. Then 7th pin number is reserved for B2. So B2 is there. You can write here 7th pin number of IC 7483. Then 8th pin number is for A2. So you can write here 8th pin number for A2. And that's S1 is 9th pin number. So you can write here 9. Then A1 is for 10th pin number. So A1 you can write here 10. Then 11 is B1 pin number. So you can write here 11. 12 is reserved for ground. So remember, 5th one is reserved for VCC and 12th is reserved for ground. And then C in is reserved for VCC. So not VCC, C is reserved for 13 pin number. So 13 you can write here. Then C out is the 14 pin number. Then S4 is a 15 pin number. S4 is the 15th pin number and B4 is your 16th pin number. Means what? Once you learn the pin diagram of IC 7483, you need to write down the pin numbers here every time. But if you want to make a connection, then you should know the connection of each and every cable of your this circuit or the connections. Yes, everyone understood this? First of all, complete this pin diagram of IC 7483 and write down the numbering as per this IC 7483 in your block diagram or the circuit diagram. Okay, complete it. Once it is done, let me know so that I can take next concept. Simultaneously give the attendance. Roll number 1,
Present, ma'am.
roll number 2,
Present, ma'am.
3,
Present, ma'am.
4, 5,
Present, ma'am.
6. Nachiket is there?
Present, ma'am. Present.
Yes. Roll number 6, Ritika. Roll number 7, 8, Ketan. Roll number 9, roll number 10, 11.
Present.
11 is present.
Yes, ma'am.
12,
Present.
13, 14,
Present, ma'am.
15,
Present, ma'am.
16,
Present, ma'am.
17,
Present, ma'am.
18,
Present, ma'am.
19, 20, 21,
Present, ma'am.
22,
Present, ma'am.
23,
Present, ma'am.
24, 25,
Present, ma'am.
26, 27.
Present, ma'am.
Whether is present? Not Pranjal, na? 28.
Present, ma'am.
Shravani.
Ma'am, 27 is present.
Yes. I have marked your attendance. 27. 29,
Present, ma'am.
30, 31, 32,
Present, ma'am.
33, 34,
Present, ma'am.
35,
Present, ma'am.
35 na?
Yes, ma'am.
36, Bhavna.
Present, ma'am.
37,
Present, ma'am.
भावना आहे का?
Yes, ma'am.
ओके. 37 आहे. 38,
Present, ma'am.
Present, ma'am.
39, 40, 41, 42,
Present, ma'am.
43, 44,
Present, ma'am.
44 का साक्षी?
Yes, present, ma'am.
Yes. 45,
Present, ma'am.
46,
Present, ma'am.
47,
Present, ma'am.
48, 49,
Present, ma'am.
50,
Present, ma'am.
51, 52, 53,
Present, ma'am.
54, 55, 56,
Present, ma'am.
57,
Present, ma'am.
58, 59, 60,
Present, ma'am.
61,
Present, ma'am.
62,
Present, ma'am.
63,
Present, ma'am.
60, 64, 65,
Present, ma'am.
66,
Present, ma'am.
67, 68.
Present, ma'am.
Okay.
Ma'am, 10 is also present.
कुठे होतीस बाळा अटेंडन्सच्या वेळी?
मॅम मी माईक चालू करायला गेली आणि नेटवर्क निघून गेलं.
ओके. Okay. So only 42 students marked their attendance, out of 48 number of candidates present in the lecture. Only 42 students are present for the lecture. Yes, have you completed this, everyone? Now we'll see the next concept here. So with the help of this IC only. Suppose purpose of this IC is what? What is the use of this IC 7483? Use of the IC is 4-bit parallel binary adder, or name of this IC is 4-bit parallel binary adder. Means this IC can be used to add two 4-bit numbers. Okay, so here we can use, or suppose if you want to use the same IC for subtraction, can you use that? Yes, anyone? Can you tell me how to use the same IC 7483 for subtraction, as we have seen the concept of 2's complement method, subtraction, binary subtraction using 2's complement method. So we can use that particular concept for this addition or subtraction, 4-bit parallel binary adder. Means with the help of the IC 7483, we can perform subtraction also with the help of 2's complement method. As we know the method or the procedure how to add or how to subtract two numbers. Input and output change. Yes, how you can change input and output, as the specific functions are given to each and every pin of this IC 7483. So we can't change input and output. Then how can you change input? Yes, suppose you want to subtract. Okay, suppose 9 minus 5. If you want to perform this subtraction, then how to perform this subtraction? You can simply find out 2's complement of 5 to get minus 5, and after that you simply add the 9 into 2's complement of 5. So here 9 can be represented by 1 0 0 1, and 5 can be represented by 0 1 0 1. Then how will you get 2's complement of 5? Just by scanning the number from left side, write down first one as it is and invert all the remaining bits like this. Okay, so this is the 2's complement of 5. After getting 2's complement, you can simply add it into 9. So 9 is 1 0 0 1. 1 plus 1 0 carry 1. 1 plus 1 0. 0 carry 1. Then 1. 1 plus 1 0 carry 1. If we are getting carry 1, then yes, then your result is positive. Just ignore that carry and your number is positive, that is 0 1 0 0, it is equal to 4. So once you perform this subtraction, you will get the exact answer 5. If you get carry 1, then your result is positive. If you get carry 0, then your result is negative. And you need to convert it into again 2's complement form, or you need to get it in a original form from 2's complement number. Okay, so you need to simply use this procedure here. But here, suppose this is 9 here, B means 9, and if here A is equal to 5, A is equal to 5. So instead of using 5 as it is, you have to use 2's complement number. Okay, 2's complement of 5. How will you get 2's complement? Just you can use 1's complement of 5. 1's complement of 5 means what? 0 1 0 1. How to get 1's complement? Just invert each number, means 0 0 1, like this. So this is the 1's complement of 5. 1's complement of 5, and after getting 1's complement, you need to add 1 into LSB bit to get 2's complement of that number. This is the procedure. Everyone knows this procedure? Yes, tell me. How
Yes,
to get
ma'am.
2's complement? Yes. So 1 1 0 1. Is it right? Yes. This one is also right. We are getting this one using direct method, and this is the indirect method. Just convert it into 1's complement and add 1 into the 1's complement number to get 2's complement number. Okay. So here, how to get 1's complement? Just by using NOT gate. Okay. So here, when you use NOT gate here, NOT gate, and if initially you give 1, then you get 0. Yes, understood. So we can pass this variable A through NOT gate. So instead of directly passing A to this IC, you can use here NOT gate and then connect. NOT gate and connect. Right? So here you can use A4, A3, A2 and A1. If you want to Give 5 here, so 0, 1, 0, 1. After giving it as input to NOT gate, you will get 1, 0, 1, 0, which is equivalent to 1's complement of 5. Yes, is it right? Everyone understood this concept? After that, you need to add 1 into this 1's complement to get 2's complement. So, instead of connecting this C in to ground, instead of connecting yes, Aditya. Instead of connecting this to ground, you can simply connect it to VCC. Ground means 0 volt and VCC means plus 5 volt, which is equal to 1. 0 and 1. In the form of binary numbers, you can represent it. So, to get 2's complement of variable A, you can simply connect that variable A through NOT gate and connect C in pin to VCC. Once you connect, you make this connection, then you can find out 2's complement of variable A, and after getting 2's complement of variable A, what we are performing here? We are simply performing addition. Once you get 2's complement of the second number, you simply have to add numbers, 2 numbers, okay? So, with the help of this IC also, we can add these 2 numbers. Just, first of all, you have to just find out 2's complement of the number, and then you simply use adder, that is 4-bit parallel binary adder for the subtraction. Yes, everyone understood this or any doubt is there? Aditya? Not Aditi Patil. I doubting Nala. Means we can make use of adder IC 7483 for subtraction also. To perform the subtraction, 4-bit binary subtraction, we can use IC 7483. As this IC is used for the addition only, but we can use it with the help of NOT gate. So simply we can pass one of the input through NOT gate and connect C into ground. That particular circuit will work as a subtractor. Yes, everyone understood this. So this is the block diagram of full 7483 4-bit parallel binary adder for subtraction. काय नाही कळलं आदित्य बोला काय नाही कळलं काय एक्सप्लेन करून हवंय
Block diagram.
यस आदित्य यू आर नॉट ऑडिबल
Block diagram.
प्लीज ब्लॉक डायग्राम हे कळलं का मी काय एक्सप्लेन केलंय ऍक्च्युली हे जे मी सांगितलंय हेच मला इकडे ब्लॉक डायग्राम मध्ये एक्सप्लेन यूज करायचं ठीक आहे सो इफ यू वॉन्ट टू सबट्रॅक्ट एनी 2 numbers then we have already seen the procedure of subtraction or binary subtraction using 2's complement method. Means here 9 minus 5 we need to perform. So to perform that you can first find out 2's complement of 5 and then add that 2's complement of 5 into 9 to get your result. And once you get carry 1, then you need to simply discard that carry, your result is positive. Okay, so with the help of that only I can explain you here. Suppose this is your block diagram of 4-bit parallel binary adder IC 7483. Okay, so that IC is having total number of pins, 16 pins. I have already explained you that the purpose of all the 16 pins. So here out of 2 decimal numbers, you can find 2's complement of any number. Okay, so here 9 we can given as input to this B and A is your 5. So to get 2's complement, you simply have to find out first 1's complement and then add 1. This is the basic procedure to get 2's complement of any number. Okay, so to get 1's complement of that number, you need to use NOT gate. So to use NOT gate here, we are just passing this A variable or A number that is 50101. We are not directly passing it to IC 7483. We are passing these numbers through NOT gate. So here 1 is connected, means 1 pin number input of this NOT gate is 1, then output becomes 0. Similarly, input of this NOT gate is 0, then output becomes 1. Then input of this NOT gate, third one NOT gate is 1, then output becomes 0. Means all the outputs are in the inverted format. or inverted form. So 1010 is a ones complement of 5, and after getting ones complement, what is your next step? You need to add 1 into the LSB bit. So for that only, here I have made these connections. That is, in the previous case, I told you that see, in every time you need to connect it to ground, that is 0 volt. But right now, for subtraction, you have to connect this C in pin to VCC. VCC means plus 5 and it is considered as 1. Okay, 0 and 1. Binary number, so 1 is considered here. So once you get 1's complement, then you simply have to add this 1 into 1's complement, LSB bit of 1's complement to get the 2's complement number. So in this way, when you make these connections, this particular circuit, that IC7483, is work as subtractor. That is 4-bit parallel binary subtractor. Yes, everyone understood this? Or any doubt you have? कळतंय का? So complete this diagram, everyone. One more question. Suppose this is your IC7483. Use of that IC is 4-bit parallel binary adder. Addition साठी use होते IC. Okay. But now we see how to use the same IC for subtraction. ते कळलंय तुम्हाला? Just by using the NOT gate and connecting one of the input through NOT gate and C into VCC, you can make the same IC connection for subtraction also. Suppose if I want to design such a circuit, that circuit will work as a subtractor or it can be work as adder also. So can you tell me how to build or how to design such a circuit? You can just think on that. I'll explain you tomorrow. Okay, so we'll stop here. Just one question, I'm repeating it. Suppose I want to design such a circuit, that circuit should work as adder or subtractor as per our convenience. If you want to use, if you want to perform addition, then you can perform addition also, or if you want to perform subtraction, then you can perform subtraction using the same circuit. Then how can you design that circuit? NAND gate.
XOR gate.
Very good, Shweta. Very good. Rohit, you are actually wrong. You can't use NAND gate here, but Shweta is right. You can use XOR gate. As you know, the truth table of XOR gate. XOR gate truth table is what? If both inputs are 0, then output is equal to 0. And if one of the input is means if inputs are changed, then only output is equal to 1. So you can use XOR gate instead of, you can use XOR gate instead of this NOT gate to make the circuit for subtraction and addition also. Okay, so I'll explain this circuit in tomorrow's lecture. So we'll stop here. Thank you for joining. If you have any query, you can ask me. Otherwise, you can leave the session. Thank you.
हॅलो मॅम.
बोला.
मॅम, युनिट टेस्ट साठी किती सिलेबस होणार आहे? किती जेवढा झाला तेवढा?
हा, जो टीच झालाय ना लेक्चर मध्ये तो सगळा असणार.
ओके मॅम. मॅम, ते टाइमचं नाही माहिती, तिथे शेड्यूल मध्ये टाइम बी दिला नाही.
हो, टाइम नाही दिलाय तर तुम्ही तो 4 o'clock ला स्टार्ट करायची एक्झाम. तसं फॅकल्टी तुम्हाला